Okay, so this problem is a combination of magnetism and a little bit of circuitry and electricity stuff too. Um, and actually, there's a little bit of thermodynamics in it as well. So there's a little bit of energy stuff in this one. So this is kind of a question I'm not sure you'd see in full in a Physics 2 test anymore because it draws on a lot of Physics 1. But there's nothing here that we haven't really covered. So I think it's still fair to review. So, with that said, let's start with parts A and B, which are the sort of setup type parts. C and D are the ones that deal with actual magnetism directly. So the first thing is we're told some information about what's moving and its initial and final states. Right? It starts from rest and it ends up at a given speed. And we're told something as well about the current, right? Because these are charged particles that are moving. So motion of charged particles is defined as a current. And we want to know, to get these protons from rest up until that 3.1 times 10 to the 6 meters per second, what potential difference do they need to be accelerated through? Well, if we're believing that energy is conserved, then we believe that initially, actually let's try this a slightly different way. We believe that the kinetic energy they gain has to come from potential energy that they lost, right? So that delta K equals delta U, right? Whatever they gain here, they lost there, or vice versa. And we know how to write kinetic energy, and we know they start at rest, so this is just 1 half mv final squared. And delta U, right, is the change in electric potential energy, because that's the type of energy that the electric potential would cause, which is Q delta V, right? And so now all we need to do is solve for delta V. We have all those other numbers. So delta V equals mv final squared over 2q. And the AP sheet has the charge of a proton on it for you, as well as the mass of a proton. You just have to be very careful in punching them into your calculator because they're right, very small numbers. That's the mass in kilograms. So if you do this in your calculator, I definitely suggest doing it in multiple steps. Do the entire denominator and write that number down. Square the speed and write that number down. Multiply by the mass and write that number down, then divide the two that you got in the end. So if you do that very carefully, you will get, this is 5.0 times, actually it's not going to quite fit in there, times 10 to the fourth volts. And that's the potential difference that's required to give it that much kinetic energy. There is another way you can do this, and that's a kinematics type approach using Newton's laws. So this way is, I think, a lot faster, right? The kinetic energy they gain is given to it by the electric field, electric potential. But you can also use that F equals ma, and then the force, this is QE equals ma. But we know there's a relationship on the AP sheet about the electric field and the electric potential is QV over D, which is how long they're in that field for, which we don't know yet. That's okay. That's why I wouldn't have expected you guys to do this way, because you have to introduce a number that's going to just coincidentally cancel. But this side tells us sort of how the potential that we travel through and how long we're in it, right? That's the potential we travel through and how long we're in it relates to how fast we're traveling and how much we speed up when we're in it. But we can also use, right, a kinematics equation, the time-independent one, that v final squared, v initial squared plus 2a times a distance, right, how long you travel. The initial velocity is 0, and so we can figure out that a is v final squared over 2d. And this, right, just goes right into there, and the d's will cancel, right? And that gets you to the same exact spot that we were. So you could do it with kinematics. I think it's a little bit harder and a little bit tougher to reason through, but if you're thinking of it that way, that does work. Energy conservation is definitely better. So that's part A. We get 5 time cents. So part B is, I think, a really detailed question that is good, right? We've talked about thermal energy a bit, but it's more of a physics 1 type thing. So I'm not sure if you ever see part B, but there are enough physics 2 type concepts I think it's worth doing, so I'll make sure to explain it. So, thermal energy. Right? Thermal energy is sort of the dumping ground for all the other types of energies. And if the protons are stopped, that means they have to lose their kinetic energy. Right? But the kinetic energy that we're able to calculate is the energy of 1 proton. So really we need this times n, however many protons you have. Okay? So let's kind of clean this up, right? 1/2 m proton v final squared, right? Those are all numbers that we know. And n is the total number of protons that travel in 1 minute, right? That's what we really need. So what we don't really know, we don't care about like whether it's 1 million protons or 2 million protons, we just care about how many in 1 minute. And that's something that's related to the current, right? The number of protons that travel in a period of time. So the total number of protons that go by is the total current times the time. That's the total amount of charge that goes by, right? Actually, I mean, we know that the definition of current is delta Q, actually let's write it as lowercase, over delta T. So this is going to help us get at it. But if we know each proton's charge, then dividing delta Q, the total amount of charge that flows, by the charge of 1 proton, should tell us the total number of protons that flow. That's what's over here. So I delta T equals delta Q. If we divide this by Q proton on both sides, so for example, if your charge that flowed was 10 times the proton's charge, then divided by the proton's individual charge would give us just 10, or the total number of protons. So this is n. And so this is why I think this is a good physics 2 question, is that this relationship is an important one to being able to solve this problem. And so this just goes right in here. So 1/2 mPvP squared I delta T over the charge of a proton. Right? And these are, again, all numbers that we know, right? The delta T is the 1 minute time interval. The mass and the charge of the proton are on the equation sheet, and the final velocity is the speed we're given, and the current is the current that we're given in the problem. So you can plug all those numbers in. I'm not going to write them all out because it actually takes kind of a lot of stuff this time. But if you're very careful putting it into your calculator, you will get 6 joules. Okay? So it's another kind of energy conservation statement, but it's also practice in sort of manipulating the definition of current and remembering exactly how it relates to sort of the amount of charge and the number of charges that move. Okay, so that's parts A and B. Now we're ready for the actual magnetism part. We have our proton beam, and it's entering a region where there's a magnetic field. And we want to know what's the magnitude of the magnetic field that causes the radius of that circular path, right? So we have our incoming beam, and then it enters that field region, and it follows a semicircular path and comes right back out or hits a wall or something. And we want that radius, right, that distance right there, to be 0.1 meters, or 0.10 meters, right? And we want to know, what does the field strength have to be to do that? Well, This is a force question in the end because we know there's a relationship between force and magnetic field. And so what we really need to do is we need to consider a free body diagram, right? If this is one individual proton at just an instant in time, then the magnetic force has to point towards the center of the circle that it's traveling in, because that's the only force acting on it, right? Otherwise it wouldn't move in a circle. So this is the magnetic force, right? It has to point towards the center of the circle. And we know an expression for the magnetic force is Q, the charge, in this case it's Q proton, V, the velocity, times B, the magnetic field strength. And we know the direction because we drew it. It's towards the center of the circle. And since it's moving in a circle, we know that A is a centripetal acceleration. It's V squared over R. And we know Newton's laws, F equals ma. So all we're going to do is we're going to put those pieces together using the mass of the proton as well. So Q proton, velocity times magnetic field, equals mass of proton times velocity squared over r. So some of those velocities will cancel, and we can easily solve for B, the strength of the magnetic field. It's kind of sloppy R there. Right? And once again, the mass and the charge are on the AP sheet. The velocity is not changing, right? The speed is not changing. The velocity is because of direction. So the speed is just whatever it entered at, that 3 times 10 to the 6 meters per second. And r is the required 0.1 meters that we had in part C. So again, you plug all those numbers in, and you get 0.32 Tesla. Right? The magnetic field units are Tesla. Okay, so finally, part D, non-calculation part. We know what direction the force must be in because we know what direction it's curving in. We know the charge of the proton is positive, so we have to use the right-hand rule. So for this, right, I'm going to redraw it, but for this proton sitting right here, remember the direction, we have to use our thumb in the direction of the velocity. So at that instant, again, just kind of copying from this picture, at that instant the velocity is like that. That is V. And the force is like that. And so our job is to figure out the direction of B. And since I've drawn these two arrows, F and V, in the plane of the page, and we know the magnetic field has to be perpendicular to both of them, the magnetic field is either upwards, straight out of the page, or downwards, straight into the page. That's the only two options that are left. Which one it is depends on the right-hand rule. Remember, you put your thumb in the direction of V, your index finger will point in the direction of the magnetic field, either up or down, and then your middle finger has to point in the direction of the force. And if you kind of rotate your hand around until it works out, you'll find the only way to do that and make it all work out is if your index finger points upwards out of the page. So given the convention, the coordinate system that we've drawn, this would be the, or they've given us rather, this would be the positive z direction, right? If you wrote out of the page, that would work. Up is probably not a good idea because up could be interpreted as towards the top of the page, which is not correct. So positive z direction is the clearest, or out of the page is probably the second best. And that's, again, there's another one. We wrote a lot of units in this. If you got all the units right, that was another point. So always keep track of your units. It's an easy way to get points. Even if you do the math wrong, if you know that you're calculating a charge or an energy or a field, get the units right, you'll get something in the end.